And now let me explain to you a little bit about what this non-deterministic polynomial means. Okay, so remember I told you there's the single tape architecture, then there's parallel tape, let's say 500 tapes. Okay, and you might have remembered I mentioned when we discussed sort of CFGs and DFAs with stack, I said that, CFGs are slightly more powerful than DFAs with stack. Okay, and in order to make them equivalent, you need to give the DFA a slightly higher capability, which is what I call non-determinism. So the non-deterministic DFA with stack is as powerful as C context-free grammars. And the same sort of thing is going on with Turing machines. So you have the single tape, you have, let's say, parallel tapes, let's say 500 or 1,000, but some fixed number of parallel tapes. There's one other architecture, but it doesn't fall into this class, and that architecture is, in some sense, unbounded parallelism. So, unbounded parallelism. That, in sort of a gross nutshell, is sort of what non-determinism allows a machine to do. It allows it to try all kinds of possibilities simultaneously. Some kind of unbounded parallelism. Parallelism, just, if I have 500-fold parallelism, I can try 500 things simultaneously. Unbounded parallelism allows me to try, many things as I want in parallel. Well, so it's unbounded parallelism. Okay. So this is what non-determinism is. Now, in the context of what we can implement in practice, we can't implement non-deterministic Turing machines. So they have not much practical value, but they have theoretical value because this level of this kind of architecture, this kind of non-determinism exactly corresponds to problems if you can solve them quickly and find the proofs, then we can easily check the proofs. So that's a very intuitive definition. This is the technical definition. Those problems can all be solved in polynomial time. So the polynomial, those kinds of problems can all be solved in polynomial time on a Turing machine with this kind of capability, on a Turing machine with non-deterministic capability. Okay. Unbounded parallelism. Now you might think, well, if parallel is equivalent to single tape, then shouldn't unbounded parallel be equivalent to single tape? Turns out we don't know. Okay. So polynomial on parallel is polynomial on single tape. Polynomial on unbounded parallel, i.e. polynomial on non-deterministic machine, is that equivalent to polynomial on single tape? We don't know. So, if you can solve in polynomial on this non-deterministic Turing machine, is it equivalent? Does that mean that there's a polynomial algorithm on the deterministic, on the single tape Turing machine? We don't know. And that is the famous question, P equals NP. P we can solve in polynomial time on the single tape machine. NP, we can solve in polynomial time on this weird machine that has unbounded parallelism, on this non-deterministic machine. Question mark. Is P equal to NP? We don't know. You solve that, instant fame. $1 million. Okay. And that's going to be, and solving this is related to something that I'm now going to discuss, which is the structure. So it turns out that these problems whose proofs are easy to verify, these problems have a very nice structure.